Hello my dear viewer, this is Science Bro. I brought for you a video on calculations about thermochemistry. Now we are going to dive into most of the calculations in thermochemistry, almost a full episode. Now if you have never subscribed to this channel, please consider subscribing to this channel. Just below the video, hit the subscribe button to receive notifications for good videos. Contact me on this number in case you are inquiring of anything or you have any comment. Now thermochemistry has a variety of calculations, and the students are always getting a problem in how to handle them. So we are going to dive into very many of them, and probably almost doing all of them. So we are going to look at number 1, finding heat of a reaction given heat of formation. Number 2, finding heat of a reaction given heat of combustion. Number 3, finding heat of a reaction given bond energies. Then number 4, finding heat of a reaction given bond energies and the atomization energies. Also going to look for the heat of precipitation, heat of neutralization, heat of displacement, then heat of solution somewhere, and some lattice energy will be talked about. Then we shall also look at energy level diagram. Now let us look at the first type of calculation. We said there are about 11. The first type of calculation is finding heat of a reaction given heats of formation of the compounds. Finding heat of a chemical reaction. Now when we refer to heat of a chemical reaction, it depends on the type of reaction. If the reaction is a combustion reaction, then we are finding heat of combustion. If the reaction is a hydrogenation one, we are finding heat of hydrogenation. So then the type of reaction gives us the type of heat we are trying to find there. Now most of the thermochemistry calculations use Hess's law to handle them. Now Hess's law, we are going to handle these types of calculation using Hess's law, but we are going to divide Hess's law into two. We are going to use by calculation and Hess's law cycles. So we shall use by calculation and Hess's law cycles. So let's dive in the first example here. Let's use Hess's law by calculation first. Hess's law by calculation. Now how do we do that? We are going to use a formula here. Let us look at the formula. Heat of any given reaction, standard heat of a reaction, we are going to sum heats of formation of the products, heats of formation of products, subtract sum of heat changes for the formation of reactants. So that is Hess's law by calculation. Now let's look at the question here. What are our products there? We have our product is carbon dioxide and water. So we are going to look to sum the heats for this and this, then we subtract for that. But keep in mind, the enthalpies of formation of all elements in their standard states or normal physical states are always 0. Let's punch in there. So we are going to have this enthalpy of formation of carbon dioxide added to that of formation of water. Then we are going to subtract enthalpy of formation of ethanol plus enthalpy of formation of oxygen. But let's look at the stoichiometric coefficients. I have 3 on oxygen, so I will multiply by 3. Carbon dioxide 2, then water 3. So let's dive into that. So I will have 2 times the enthalpy of formation of carbon dioxide is this. So 2 times negative 393 plus 3 times that of water, negative 286. Then I'm going to subtract that formation of ethanol. It's only 1 times that of formation of ethanol. We can write the way it is, negative 275. Plus for oxygen, we said it is 0 for all elements in their normal physical states. So we are going to just have our calculator here. So we're going to have, that will give us negative 1369 kilojoules per mole there. So that is basically the answer. Now this answer has a bearing. We can comment on this answer. And now for heats of reactions, they indicate whether the reaction is feasible or not feasible, spontaneous or not spontaneous. So this reaction is very feasible or spontaneous because the heat of reaction is negative. Let's look at method 2, Hess's cycles as a method. So how do we use Hess's cycles? So Hess's cycles. These are also called enthalpy cycles, or we call them thermochemical cycles. And sometimes many examiners have also incorporated into call them Born-Haber cycles. So any of those can be the names for that type of method. So Born-Haber cycles, thermochemical cycles, AC0 cycles, enthalpy cycles. Of course, Born-Haber cycle has developed basically for ionic solids, but has been extended to also covalent compounds. So in handling heat of a reaction given formation values, so the Hess cycle is standard like this, provided you are given formation values. So we have all arrows point into forming, because reactants and products are what we are having as the compounds that we are forming from the elements. Now, we look at our question here. We are given ethanol, this and that, so we transpose that. So this is C2, H5, liquid plus 3 of the oxygen, giving us 2 carbon dioxide plus 3 waters. Now the elements we can check on the compounds. Here I have ethanol. So ethanol is formed from carbon, which is a solid, oxygen, which is a gas, and hydrogen, which is also a gas. So if I first balance that, I have 2 carbon atoms. Of course, both sides are balancing. Then I have about how many oxygen atoms? I have 7 oxygen atoms, so I can have 7 out of 2. This is 6 plus 1. That gives us 7, which is the same. 4 plus 3 is 7 oxygen atoms. So hydrogens are 6. Even here, hydrogens, I have 5 plus 1, 6. So multiply this by 3. Now point into ethanol. We can't point into an element because we can't form elements. We can only form compounds. So I have 2 compounds. I can draw 2 arrows from anywhere this side, or I draw an arrow pointing in the middle here. That is Hess's law. Hess's law says that the heat of this reaction in this step, the enthalpy change that leads to the formation of this is got from these values. No, we are not necessarily summing this, but we are going to see how we handle it here. So this is standard heat, this reaction, standard heat of this reaction. Now, since it's a combustion, we are burning, and call it enthalpy of combustion of ethanol here. Now we can also draw 2 arrows. We can, of course, put 2 arrows, or basically, and put one pointing to that, then one pointing to that, from anywhere this side into that. So let's punch in those values, or you have 1 arrow and put all the heats on 1 arrow there. So formation of ethanol is negative 275. So we have formed 1 mole here. So this means formation value negative 275. Formation of carbon dioxide, I have this, but you have formed the 2 moles. So this is 2 times negative 393. Then for water, I have 3. I formed 3 molecules, negative 286. Now, when we are handling this, the easiest way to memorize is that you look at all clockwise arrows and add them to clockwise arrows and anti-clockwise to anti-clockwise. So you can see that this arrow goes this way. Even this arrow, if you try to follow, this goes in the same direction like this. So these are together and these are also together. So I'm going to say heat of, standard heat of combustion plus negative 275 is actually equal to these ones here, 393. 3 times negative 286. So on making this the subject, which is negative 1369 kilojoules per mole. So this reaction is feasible because the heat of this reaction is actually exothermic or negative. Let us look at example 2. The table below shows the heats of formation of some compounds, that's ammonia, nitrogen trifluoride, ammonium fluoride. Calculate the enthalpy change for this reaction. So let's first use Hess's law by calculation. So Hess's law by calculation. So in this case, we said use the formula. So standard enthalpy change for any reaction is equal to summation of delta heats of formation of products minus delta heats of formation of reactants. So we are going to punch in the values. So I can see that my products are this and this. So I'll have a heat of formation of NF3. Then I'm going to add it to 3 delta heat of formation of ammonium fluoride. Then we are going to subtract for the reactants. So I have 4 times enthalpy change of formation of ammonia, then plus fluorine has a 3 times delta enthalpy change of formation of fluorine here. So I substitute the values. Ammonia is negative 46 plus 3 times for ammonium fluoride, that's negative 467. Then we are subtracting for ammonia. This was ammonium fluoride, I think, is in the products here. So this is not ammonia, so this is for ammonium. That's nitrogen trifluoride, which is negative 114. Then this is for ammonium fluoride, which is this. So this is for ammonia, which is 4 times for ammonia. That's negative 46. Then since all elements, like fluorine in its standard state, the enthalpy formation is 0, so 3 times 0. So I punch that in the calculator. That now gives us negative 113 kilojoules per mole. Let us look at method 2 using Hess's cycle, or what we call Born-Haber cycle commonly. So Hess's cycle, Born-Haber cycle, or enthalpy cycle. Now we look at the equation given to us, that is for ammonia. Make sure it's balancing, otherwise we can get wrong results. Giving us 3, then plus 3 of this. So we said you point into elements that are forming this compound. So this has nitrogen and hydrogen. So nitrogen is a gas. Elements, they are standard states. Then I can see fluorine here. So these are the key elements that are in these compounds here, in these compounds here, in these compounds here. So I have seen fluorine, nitrogen, and hydrogen there. So we point into this. So because this is formed from these elements, So you can have two arrows, one there, then one here. You point the arrows from anywhere this side into those. So we can't point it fluorine because it's not formed from these ones. So this is the heat of the reaction. So I feed in the values. So let's first balance. This nitrogen is 4, I put here 2. Hydrogen is 12, so I put here 6. Then fluorine this way 6, put here 3. So even this side balances automatically. Now we look at these values here. So I formed the 4 of ammonia, that is 4 times negative 4, 6. Then I formed one of this, so that just write that. So I formed the 3 of this. So this is 3 times negative 4, 6, 7 here. Now we said that you can look at all arrows going anti-clockwise and add to those arrows going anti-clockwise added together, then those going clockwise added together. Then anti-clockwise energies are equal to clockwise energies. Or rather, you can make this energy to be the total of all these by modifying these arrows. So by observation, this is going in the same direction with this, and these are going anti-clockwise, clockwise, then this also clockwise. So it can be delta heat of reaction plus this, the 46 equaling to this one plus 3 times negative this one. So finally, you must be able to solve that expression and receive negative 331 kilojoules per mole there on handling that calculation. But students get trouble in handling these arrows. You can always get this in terms of this by making this to all go in the same direction. So since this is going this way, I can make all this face downward. So we reverse this. So that's another way. Reverse this, then you reverse this energy here. So I've reversed this energy here. So that will be the alternative to that question there. So you have it as now this one is equal to these ones here. So that is 4 times 46 plus negative 114 plus 3 times negative 46. That gives me negative 113 kilojoules per mole. Double check that calculation. Let us look at category 2. Now in category 2, we are going to finding the heat of a reaction given heat of combustion. Remember, we are from calculating the heat of a reaction given heats of formation. So here we are looking at if you are given combustion values, what do you do? So we are going to employ two methods. We are going to use Hess zero by calculation. Then we shall use Born-Haber cycle or Hess cycles. So let us dive into the question. First method, method 1, Hess zero by calculation. So under this method of calculation, we extract the given equations and the required equation from the question. So let us see. The standard enthalpy of combustion of propan 1 also, you are going to write the equation for combustion of propan 1 or carbon and hydrogen. Let's write that. So this is the given equations. So let's burn propan 1 or. Remember, we burn 1 mole in each case. So plus oxygen gives us carbon dioxide plus what I call this heat value and the enthalpy 1 and call this equation 1 because of space. So let's balance the equation. Our carbon is, there are 3 carbon atoms. There are 8 hydrogen atoms, put 4. There is 10 oxygen atoms, put 9 out of 2. So 9 plus 1 gives us 10. Let's also burn carbon. So this is carbon plus oxygen gives us carbon dioxide. So call this standard enthalpy change 2 and call that equation 2. Then combustion of hydrogen. So this is going to be hydrogen plus oxygen gives us water. Call this standard heat value 3. So let's balance this equation. We don't multiply this value, this We don't multiply hydrogen by any factor because we burn strictly 1 mole. According to the information in the question, enthalpy of combustion is the heat given out when you burn 1 mole of a substance. So I put here half. Now what do they want? Calculate the standard enthalpy of formation of propan 1 ol. So we write the equation for formation of propan 1 ol. So required equation. So we are required to write how propan 1 ol is formed. So propan 1 ol contains carbon, hydrogen, and oxygen. So write all elements in their normal physical states. Oxygen is a gas, hydrogen is a gas, carbon is a solid. So you get propan 1 ol. So this is what we want. So this is the formation value we are looking for. So there are about 1, 2, 3 carbon atoms are 3, hydrogens are 8, oxygen is 1, put a half here. Now what we see, we observe our required equation and compare it with the given data here. So we can manipulate this to receive this, and that will be enough to calculate the enthalpy of formation of this reaction here. So you can see carbon is on my left, so this is equation 2. So it is 3 of equation 2. 3 of equation 2 plus 4 hydrogen, which is equation 3. So for equation 3. Then I can see we don't bother about oxygen, it comes automatically. So then this is reversed. Propan 1 ol is on my right, yet it's on my left, but stoichiometric coefficient is 1. Stoichiometric coefficient is 1. So I'm just going to reverse this equation, turn the other way around. So by reversing an equation, we're actually going to subtract. So say minus equation 1. Minus equation 1. So standard enthalpy of formation, we are going to just have 3 times the value for equation 2. So 3 times delta this value plus 4 times this value. Then I'm going to subtract this value for equation 1. So substitute those values. This is combustion of carbon is negative 393 plus this for hydrogen, which is negative 286, then minus this for propan 1 ol, finally yielding me. So this is going to be negative 313 kilojoules per mole. Now it indicates this value has a meaning on the equation that we are given here. So we are given the equation for formation of propan 1 ol. Enthalpies of formation are used to predict the stability of the formed compound. If the compound is formed endothermically, then it's unstable, but if it's formed exothermically, like for this case, then it is stable. So the comment could be propan 1 ol is stable because the heat of formation is negative. Now, some students might be interested in finding out how did these equations yield for you this one. You can go ahead if you have enough space to show how this expression turns into this one. So you can roughly grab here. So, but the simplest way is to stop there. But of course, you'll be calling this equation down. So 3 of this plus 3. So you multiply everywhere by 3. Gives us 3. Then this delta value will be multiplied by 3. Then you go to this equation. This is 4 for this. So 4 of this plus 4. This gives us 2. Then 4 of water here. So 4 times delta heat 3. Then we are going to subtract this. To subtract is to reverse this equation. So I'm going to reverse this. So I'll have 3 of carbon dioxide plus 4 of this. So I'm starting this way, turning the other way. Then giving us propan 1 all liquid plus 9 out of 2 oxygen. Then we add them mathematically, since this is already subtracted by reversing. So I will have carbon dioxide die into this water, going oxygen is 3 plus 2, 5 minus 4.5. That gives me a half this way. So I'll have 3 carbon plus 4 of this, then plus a half gives us what's remaining is propan 1 all. So by reversing this, this value was meant to be -3 standard heat 1 here. So this is propan 1 all liquid. So you would have it computed as this value will equal to this plus this, got 3 of this value plus 4 of this value, then subtract this value. So it will yield the same answer, but this is kind of a waste of time because we are repeating this same work here. Let's look at method 2. In method 2, we said we are going to use Hess's cycle or Born-Haber cycle, which of course seems to be more simpler and the shortest method than the other one. So here we want to write one equation. Now, before you engage into this method, let me give you the general format of the method. So the method should have reactants giving us products. Then since we are going to burn, we should have also products of combustion here. Products of combustion from both reactants and products. But many students make mistakes. Remember when we were dealing with heats of formation, the arrows pointed, these were elements, the arrows pointed into reactants and into products. But here we are pointing into products of combustion, since reactants are bound to give some product, even these are bound to give some substances here. So let's look at our question. So the standard enthalpy of combustion, they have given me combustion for propan 1 all, but we are interested in only the required equation, which says calculate the standard enthalpy of formation of propan 1 all. I just write the equation for formation of propan 1 all. Let's write it. So propan 1 all is formed from carbon, hydrogen, and oxygen. So we shall be getting propan 1 all. Say liquid. Now I'm looking for this enthalpy change here. So we balance the equation first, 3, 4.5. Now after balancing, we look in the question, we are given combustion of carbon. So when you burn carbon, you get carbon dioxide. So we first balance this with the 3. How many oxygen atoms? 6. So I'll have 3 of oxygen molecules. Then put this sign. If you burn hydrogen, you get water. But there is a 4 here. So put a 4. Total oxygen is 4. So it gives me 2 times this. Let's put these heat values here. So we burnt 3. So we multiply this heat by 3, since the heat values given are for only 1 mole. So you have burnt 4. So 4 times this heat value, -286. Of course, we can't burn oxygen. Then combustion of propan 1 all gives us this. We can also use one arrow from all of them into this, just a single arrow in the middle of them here, or we can show arrows from both, no problem. So here I'm burning this. So I've burnt 1 molecule here, but total oxygens formed in the products are 10, but I already have 1 oxygen atom here, so I need 9. So this is 9 out of 2 oxygens. But let's put that here, since I've burnt 1 mole to form this, just indicates that So you look at the stoichiometric coefficient on what we are burning here. If it's 1, you leave the heat value. Now we say the arrows facing these AC cycles have a pattern that you look at arrows going clockwise and those going anti-clockwise. So I see this and this going clockwise, then this and this going anti-clockwise. So this plus this formation value plus this, so it's as if saying minus this, which plus negative this, you can have that mathematically, which of course remains minus. So this is going to be minus this, giving us this value 393 plus 4 negative 286. Of course, which on simplifying gives you negative 313 kilojoules per mole. Now, some students can be confused with this kind of arrangement, and I always encourage that students can decide that all this heat through a single step here can be made as a sum of the heats in other steps which are below the equation here. So we can as well make sure all arrows here go in one direction, and this goes clockwise, this goes anti-clockwise. So can reverse this. So I can remove this. Then I reverse this arrow. When you reverse this, you reverse this heat. So this is the sum of this plus this plus this. So that's one way of being a bit direct. Negative 286, then plus this. The same answer. Negative 313. Ensure this sign is there. This sign should be there, and the units must be included there. So this is the method 2. Let us look at example 2. The table below shows the enthalpies of combustion of carbon disulfide, carbon and sulfur. They are here. So calculate the enthalpy of formation of carbon disulfide. So you write this equation. So let's use the first method, the Hess's law. Hess's law by calculation. So under this method, we have to write all these equations. So we can look at burning carbon disulfide. So carbon disulfide. Okay. Given equations. So we have carbon disulfide is a liquid, burn it. We get carbon dioxide plus sulfur dioxide. Call this enthalpy change heat 1 and call this equation 1 here. So you can balance it. There's one carbon atom, 2 sulfur atoms, so we put 2. Making oxygen is 6, so we put a 3 here. And I think that obviously balances. Now let's burn carbon. If you burn carbon, we get carbon dioxide. Call this standard enthalpy change to equation 2. Then we burn sulfur here. So if you burn sulfur, so we get sulfur dioxide gas. Call this standard enthalpy heat 3. So let's also write now the required equation. Calculate the enthalpy of formation of carbon disulfide. So we form that. So check required equation. Required equation here. So we are required to write equation for formation of carbon disulfide. So carbon disulfide comes from carbon and sulfur, giving us carbon disulfide liquid. So we are looking for this formation value. The reaction might not necessarily be a formation 1, but you depend on what the question is asking. So write what you want. So we can't balance this way, balance this way with the 2. So it can be a hydrogenation reaction. So you write according to the question. Now let us try to manipulate these equations to look like this one here. So you can observe that this equation has single carbon here. So this equation does not have a stoichiometric coefficient on carbon. So even here, so I'll say equation 2. So this is equation 2. Then this sulfur has a 2 multiply this equation. So 2 equation 2 times equation 3. Then this carbon disulfide is placed on the other side. So I reverse this. So I say minus equation 1. So the required value is going to be this heat of equation 2 plus 2 times the heat for equation 3. Then I subtract the heat for equation 1 here. So heat for equation 2, combustion of carbon is negative 393 plus combustion of sulfur, which is negative 294. So subtract combustion of carbon disulfide, this is negative 1102. So you punch the calculator, gives us 121 kilojoules. So positive, so we indicate this positive sign here. So this equation shows that the formation value for carbon disulfide is a positive. So the comment would be carbon disulfide is unstable because it's formed endothermically. So this predicts stability. Let's go into method 2. So in method 2, we are using Born-Haber cycle or Hess cycle. Call it Born-Haber cycle, we call it Hess cycle, thermochemical cycle, or enthalpy cycle. Now we just try to extract out what they want, calculate the enthalpy of formation of carbon disulfide. So I write the equation for formation of carbon disulfide. So it's formed from carbon, sulfur. It's formed from carbon and sulfur, so we balance it with a 2 there. Now I look into my question here. They have given me to burn carbon. So it said put here the products of combustion. So this is carbon dioxide. Plus when you burn sulfur, you get sulfur dioxide. So when you burn this containing carbon and sulfur, you receive carbon dioxide and sulfur dioxide. So this arrow points into this, so we balance this by 2. So oxygens here are this, then oxygen molecules are this for that. So here we are burning 1 mole, so we write the value as is negative 393. For this case, we multiply by 2 because we burn 2 molecules, 2 moles of this. So 2 times negative 294. Then this is the formation value we are looking for. Then this value is negative 110. So 112. So what we do, I'm going to just make sure I reverse this. Instead of bothering this plus this would be equal to this and this. So I'm just going to reverse this and make this positive. Then it will be this will equal to this plus that. So this negative 393 plus 2 times negative 294 plus 1002, which gives us positive 121 kilojoules per mole. Let's look at example 3. Now, example 3, the enthalpy of combustion of ethane is this, and that of ethanol is this. Calculate the enthalpy change for this reaction here. So let's use the first method of calculation, method 1. Hess's law by calculation. Hess's law by calculation. So what we do, we just extract out the given equation. So we have been given enthalpy of combustion of ethane. So we burn ethane. So ethane, remember we burn 1 mole. So we shall get carbon dioxide plus water. I'm going to call that standard heat value 1 and call that equation 1. So let's balance it. So I have 2 carbon atoms. Then I have two hydrogen atoms. Hydrogen atoms are balancing. Oxygens are about 5 here. So I put 5 out of 2. Now combustion of ethanol shall also burn ethanol, the liquid. So burning oxygen shall get carbon dioxide plus water. So this is delta standard value 2, call it equation 2 here. So there are 2 carbon atoms, we balance with the 2. There are 4 hydrogen atoms, balance with the 2, giving me 6 oxygen atoms. So I have 5 out of 2. So that this is 5 plus 1, giving us 6 here. So what do they want? So required equation. The required equation is already given here. So we have C2, H2 gas plus water, liquid, giving us ethanol, liquid here. So what we do, we look at how these equations, these two can change into that. It's just that this equation for ethane is on the left, while ethanol is on the right. So I just have to reverse them. I will say equation 1. So that means equation 1 plus, because this is ethanol is on the other side, so I'll say minus equation minus equation 2. So if you added them that way, they will yield this equation automatically, but it's just a repetition. You are repeating yourself. So we are just going to have this heat change for this reaction. Delta heat change for this reaction is just going to be this heat for combustion of ethane, which is this, negative to this. I'm subtracting this one here, 1160. That gives us, so that's negative 100 kilojoules per mole. So that is method 1. Let us look at method 2. So in method 2, we are using Born-Haber cycle or Hess cycle. This is how we do it. So we just pick the required equation here. So we have been given this one as what they require us to find. So this is ethane plus water giving us ethanol. So we are interested in looking for this enthalpy change for that reaction there. So they have given us combustion value for ethane. So when you burn ethane, you get carbon dioxide and water. So the arrow would be from here, but since we need the total number of atoms on these equations to be balanced together, we are going to put the arrow in the middle here. So that carbon atoms are 2, hydrogen is 2 plus 2, giving us, first I put here 2. This total hydrogen is from both of them as the sum. Then oxygen atoms are, this is 4, this is 6. So this is already 1, so I need 5 of them. So this is the enthalpy value for ethane is negative 260. Then combustion of this ethanol gives me this value negative 1160. So let's look at the oxygen atoms used here. So this is 6 already, there is 1 here. That means I'll also have 5 out of 2 here. So this heat value can be generated from these two, but you can either add this plus this to yield this. So you can say this plus this to give you this value, or we would use the other way around by reversing this arrow so that this is equal to this and that. So that would be better. So these are going anti-clockwise, this is going clockwise. So it will be equal to this plus, so we make this reversed, so giving us negative 100 kilojoules per mole. Remember that this reaction can be predicted using this. This is not formation, it's just another reaction, so the reaction is feasible because the reaction takes place exothermically, meaning that the products are normally at a lower energy level than the reactants, ensuring that the reaction can then take place. Let us look at example 4. The enthalpies of combustion of some substances are given below. We have hydrogen, benzene, cyclohexane. Now the question wants to calculate the enthalpy of hydrogenation of benzene and that of cyclohexane and comment on our results here in A. So let's start with for benzene, but we are going to use two methods, Hess0 by calculation and then Hess cycle or Born-Haber cycle. So benzene is actually this structure. Make sure you draw it well. This is being drawn roughly to explain something. So you get a saturated product, which is cyclohexane. This is about C6H6. This is C6H12. So basically, we shall need to balance the equation by 3 here. So we can now know that we have benzene, hydrogen, and cyclohexane. So I'm going to write the combustion equation for benzene, combustion equation for hydrogen, combustion equation for cyclohexane. So benzene is burnt by this equation. So when we burn benzene is a liquid, we get carbon dioxide plus water. We can call this heat 1 and even call it equation 1 here. Then we balance it. Carbon is 6, hydrogen needs a 3. So making oxygen, this is 12 plus 3, 15. So that's going to be 15 out of 2. Now let's also write for hydrogenation of hydrogen, for combustion of hydrogen rather. So hydrogen plus oxygen. So I'm writing as a balance. This gives us water as a liquid. So this is going to be heat 2, and I'm calling it equation 2 here. So let's write for for combustion of cyclohexane. So cyclohexane was C6H12. When we burn it, also receive carbon dioxide plus water. So we call it delta heat 3. Then we call it equation 3 here. Now let's balance it. This is 6 carbon atoms. Hydrogens are about 12, so put here 6. So making oxygen, this is 12 plus 6, that's 18. Put here 9. So that balances the equation. Now, what do we want? We want to write the equation for hydrogenation of benzene. So benzene is C6. So required equation. Of course, these are given equations. Required equation. So I want hydrogenation of benzene. So benzene plus hydrogen gives us cyclohexane, liquid here. So put here, that is balance the equation by 3. So I want this standard enthalpy value for hydrogenation of benzene there. So what I do, I just have to manipulate these equations to give me that, which is very easy. So what am I saying? I'm saying benzene this way. So it's this equation. So that will be equation 1. Now what am I adding? 3 times this one. So 3. Equation 2. Then cyclohexane is the other side. So I'm going to reverse this. So minus equation 3. That means the enthalpy of hydrogenation of benzene of C6H6 becomes
equation 1, which is delta enthalpy standard value, equation 1, plus 3 for equation 2, standard enthalpy value for equation 2, then minus this one for equation 3. So that is going to be, so punch in these values. So for combustion of benzene is negative 3268. Then plus for hydrogen, that means for hydrogen is negative 286. Subtract for cyclohexane, that means I'm adding this. We are reversing, of course, 320. So I put it in the calculator here. So this is negative 206 kilojoules per mole. So let's look at method 2. In method 2, we are using Hess cycle or Born-Haber cycle. So let's dive into it. So we only need the equation for the reaction wanted. So we want enthalpy of hydrogenation of benzene. So let's write the equation for hydrogenation of benzene. So plus hydrogen, the three of them, giving us hydrogenation of benzene yields for us cyclohexane. Now when we burn benzene, we get carbon dioxide plus water. So this alone gives carbon dioxide and water. Even this alone gives carbon dioxide and water. Now the hydrogen gives water. So water is coming from here and here. So those will be a bit confusing products. How much came from here and there. So what we do, we just use one single arrow from both of them. We can draw it in the middle, showing into this, then one arrow into that. So if we don't use, if you use two separate arrows from here, there will be a challenge in how much oxygen, in balancing the oxygen atoms there. So one is enough. So we are going to look at this. This is hydrogenation value. So this one, combustion of cyclohexane, gave us negative 3920. Then for this case, we have burnt 3 moles of hydrogen, so I'll multiply by 3. Then we burnt 1 here, so this will be negative 3. Benzene is negative 268 plus 3 for hydrogen, which is negative 268. So total oxygens, we can just balance the equations. So carbons are 6, hydrogens we have 6 plus 6, that's 12. We can even see it from here, it's the same number 12, so this will be 6 here. Now oxygen atoms used, we are seeing that I have 12 plus 6, that means you have used about 18. Even here it will be the same, so this will be 18 oxygen atoms. So this is 12 plus 6, that's 18. So that is the what we want. So enthalpy of hydrogenation of benzene, would actually be this. So to avoid mix up of arrows, of course clockwise I have this and this is equal to this. So to avoid that, I can reverse this arrow, then put a positive here, so that this and this are both anti-clockwise and this is clockwise. So this will be negative 3268 plus 3 times negative 286, then plus 3920, giving me actually the negative 206 kilojoules per mole. That is the enthalpy of hydrogenation of benzene. Let's look at that one of cyclohexene. So for cyclohexene, let's use Hess's law by calculation. So cyclohexene is this. Cyclohexene is this. So if we are hydrogenating it, we are actually going to get cyclohexane, which is C6H12. This is C6H10 if you count the carbon atoms and the hydrogen atoms. So I'll need the combustion equation for cyclohexene, hydrogen, and cyclohexane. So let me use molecular formulas to handle that. So let's look at equation for combustion of cyclohexene, which is plus oxygen. This gives us carbon dioxide plus water. So I'm going to call this delta heat 1, call it equation 1 here. So we balance it. So carbon is 6, hydrogen is 10, so we put here 5. That makes us to have oxygen as 12 plus 5, that's 17. So this will be 17 out of 2. Now let's look at combustion of hydrogen. So if we burn hydrogen plus oxygen, we are getting water. Let's call this delta heat 2, and we call it equation 2 here. Let's now look at combustion of cyclohexane. Cyclohexane, because it's one of the it's the product when you hydrogenate cyclohexene, you get cyclohexane. So write its equation of combustion. So I still get carbon dioxide plus water. Call this delta heat 3 and call it equation 3. So carbon is 6. So let's try to make it 6 here. Hydrogen is 12. So have this one as 6 here. So making oxygen 18. So I put 9 here. So now let us look at the required equation. We are calculating enthalpy of hydrogenation of cyclohexene. So required equation is actually hydrogenation of cyclohexene. Cyclohexene is this plus hydrogen. We get cyclohexane. Okay. Now we balance it. It's already balancing. So what I do, I look at this equation and manipulate this. So I have 1 mole of cyclohexene. So I'm going to get equation 1. So this is equation 1. Now plus hydrogen, this is equation 2. Equation 2. Now since cyclohexane is the other side and on this equation it's on the left, so I subtract or I reverse. To subtract is to reverse. So minus equation 3. So I'm going to follow that. So the delta heat value for this hydrogenation of this cyclohexene becomes delta heat 1 standard plus delta heat 2 standard minus delta heat 3. So I'm just going to have the enthalpy of combustion of cyclohexene is this negative 3752 plus that of hydrogen is negative 286. I say minus 286. Then minus or the reverse of for cyclohexane. So cyclohexane value is minus, so it becomes positive 3920. So gives us what? Let's punch the calculator here. 118 kilojoules per mole. Let's also use Hess cycle or Born-Haber cycle for this. Now in using Hess cycle, we just need to write the equation for hydrogenation of cyclohexene. So cyclohexene is C6H10 liquid, hydrogenated, we get cyclohexane liquid. So they have given us combustion values. So combustion of cyclohexene gives us carbon dioxide plus water, and also combustion of hydrogen gives us water, so mixed products from both of them. So this also produces carbon dioxide and water, but we can try it first balance. So this is carbon is 6. You use the total for both. Hydrogen is 10 plus 2, that's 12. So I just need 6 here. Even here it balances automatically. Carbon is 6, hydrogen is 12, that balances us. So oxygen is 12 plus that, that's 18. So I need 9 oxygen here. Then this is enthalpy of hydrogenation, standard value Here I use one arrow to avoid a lot of confusion. So it's one arrow and total the heats. So the heat for combustion of cyclohexene is this value, 3752, plus that one for hydrogen is negative 286. Then total oxygen is used. We just add them, these 18 oxygen atoms, that's 9O2, that's here. Then for combustion of cyclohexane is negative 3920. So I can reverse this and becomes positive here. So that this is the sum of this. So delta hydrogenation value is equal to negative 3752 minus 286, then plus 3920, giving us negative 1118 kilojoules per mole here. So we have answered part A. Let's look at part B. Part B says comment on your results in A. What were our results? Our results were enthalpy of hydrogenation of benzene was negative 206. Enthalpy of hydrogenation of cyclohexene was negative 118. Now, since cyclohexene has one bond, one double bond, benzene has 3 double bonds, we would expect that when you hydrogenate benzene, you are actually hydrogenating 3 bonds in benzene, which is equivalent to multiplying the enthalpy of hydrogenation of cyclohexene by 3, because this has 1 bond. So we would expect that when you multiply the enthalpy of hydrogenation of cyclohexene by 3, you would have got negative 354, which should have been this value. So, however, the enthalpy of hydrogenation of benzene is expected to be 3 times the enthalpy of hydrogenation of cyclohexene, which should be this. However, the calculated value, this, is lower. Reason, this is because cyclohexene contains 1 localized pi bond, while benzene contains delocalized pi bonds, 3 of them, giving it extra stability with a stabilization energy of this minus this value, giving us this energy value. Let us look at more examples using Hess's law by calculation. So the question says, the enthalpies of some reactions are given below. They've given us this, and that. Calculate the enthalpy of formation of sodium oxide. So let me write the equation for formation of sodium oxide first. Required equation. So I have sodium oxide is formed from sodium and oxygen. So this is the required equation. I don't balance this way because I must form 1 mole. Now let's follow the equations logically. If the equations are many, try to rewrite them down here as you manipulate them to avoid any mistakes in the stoichiometric coefficients. So I have 2 of this sodium. So I look for sodium. This has sodium, but I'll multiply it by 2. So let's multiply this equation by 2. So that will be 2 times equation 3. So I put it down here. So 2 of this plus 2 of this, that gives me this, giving me 2 everywhere. Give me sodium oxide, hydroxide, aqueous. 2 of this gives me pure hydrogen. So this delta H value will be multiplied by 2. So this will be 2 delta H value 3. So let's look at the other equation that, because I have 1 or 2 things, this and this, so I'm going to look for the equation having sodium oxide. So I'm reversing this. So just reverse down here. So start with this. So sodium. So that means minus equation 1. Minus equation 1. So I get sodium oxide plus water liquid here. So I'm reversing this value. So it's going to be negative delta H1. So we can see that these two equations, when put together like this, it has created for us sodium hydroxide aqueous and sodium hydroxide solid. So there is this equation 2, which I'll use. So since the solid is on the left, I will reverse this. So it is minus 2 of equation 2. So I put twice this, but reverse it. So I start with this aqueous, giving us 2 sodium oxide solid. Then this is minus 2 delta heat 2. Then let me look at what's missing. I can see hydrogen here, so hydrogen is on this equation. So I'll just drop it down here. So plus equation 4. So that will be hydrogen plus a half oxygen gives us water. So it's going to be delta heat 4 direct. So add the equations accordingly. So when I add this, so I can see sodium aqueous cancelling this aqueous, solid here. Then this water, I have this water and this water, there are 2 waters cancelling with this water. Then hydrogen is going with this hydrogen. So that means I will have 2 sodium oxide solid plus a half oxygen gives us sodium oxide solid. Then this delta heat of formation value is going to be the sum of all those. So enthalpy of formation is going to be 2 of delta heat 3 minus delta heat 1 minus this one plus delta heat 4. So it's going to be 2 times heat 3 is negative for this. Then plus, where there is minus, we are reversing heat 1. So it is plus 205. Then plus 2 times 56.5. Then plus the last heat 4, which remains negative 285.5. So we put that in the calculator and see what we get. That's negative 78.5. So we can realize that the enthalpy of formation is negative. That means we can comment and say sodium oxide is stable because the enthalpy of formation is negative. Let's look at example 2. The enthalpies of some reactions are given below. This reaction, this reaction, this reaction, this reaction. But some of them have different states, liquid, aqueous, and so on. So calculate the enthalpy of formation of anhydrous zinc sulfate. So let's dive into that. So you first have to look at the required equation. So what do they want? Enthalpy of formation of anhydrous zinc sulfate. So it is formed from zinc. So you use elements in their standard states. So zinc sulfate anhydrous, that means it's formed from elements and should be a solid there. So we want this enthalpy of this reaction, mention of that. So we are going to just play up with the equations, but let's first balance this. So there is oxygen 2. Now by looking at the equation, we can call this equation 1, this 2, then this 3, then this equation 4. Now let's look at what's available here. I have this, and as the guiding areas. So I look for zinc. Zinc is found in the last equation here. So it's on the left, and here it's on the left side of equation 4. So equation 4. Now let me look at sulfur. Sulfur is in equation 1. There is no multiplier factor here. So plus equation 1. Now zinc sulfate solid, we can find it here in equation. So zinc sulfate solid, I can observe it in this equation 3. So I can reverse this because it's on the right. So minus equation 3. So I've arrived there. Now what do I see? Let me first list this equation 4. This is equation 4 is here. Sulfuric acid, aqueous plus zinc, giving us zinc sulfate, aqueous plus hydrogen. And this remains the way, delta 84, standard value. So sulfur is in equation 1, so write equation 1 the way it is, hydrogen plus sulfur plus oxygen gives us sulfuric acid, but the state is very important, liquid. So maintain this value and then hit 1. I've not done anything to it. So what I can observe here is that I see some zinc aqueous appearing on the right here, then sulfuric acid aqueous here. So I can look at zinc aqueous in this equation. So, and my zinc solid is also on the other side. So I can reverse this equation here. So I'm going to reverse this, so minus equation 3. Last equation, so I reverse this. So this zinc sulfate aqueous giving us zinc sulfate solid plus aqueous here. Of course, some don't encourage aqueous to be in brackets, but the way the question has come, we put them in the brackets that. Let's look at what's missing here. Sulfuric acid aqueous is on the left. Sulfuric acid aqueous is on the right. So I have equation 4, equation 1 maintained, equation 3 was reversed, then equation 2 was maintained. So I'll have this remaining parts as zinc plus sulfur plus oxygen, 2 of them, giving us zinc sulfate and hydrous solid. Then this delta heat formation that I want. So formation value is going to be delta heat 4 plus delta heat 1, then minus delta heat 3, then plus delta heat 2. So standard values, so you're going to get it 4. Then this value negative 15, 3.1 plus heat 1, negative 411. Then this is reversed, heat 3 is reversed, that is 81.9. Then this one is not reversed, heat 2 is not reversed, 911. So you punch the calculator and see that value, negative 139.6.2 kilojoules per mole, of course. So do the double check of that in case of any error. Let us look at category 3. Finding the heat of reaction given bond energies here. So how do we find heat of a reaction given bond energy? Still 2 methods. The first method, we are going to use Hess's law by calculation. Then we are also going to use what we call Hess's cycles or Born-Haber cycles. So let us start with by calculation, Hess's law. By calculation, here we shall use a formula. So we are going to use a good formula here which says heat of a reaction is equal to summation of bond energies of bonds broken. Bonds are broken in reactants minus summation of bond energies of bonds formed. And they are formed in the products. So let's look at our reaction here. Gaseous ethanol burns according to the equation. So we have to show the bonds present here. So I'll have ethanol. So ethanol is this. So this is structure of ethanol. So gaseous ethanol, looking at oxygen has a double bond, but it's 2.5. Then I'm forming water. Water is like this. So it has a 2. Then I also have carbon dioxide. So carbon dioxide is like this. So that is carbon dioxide, like that. So let's look at the bonds that are there. So heat of this reaction will equal to summation of bond enthalpies of bonds broken. So they are so it's we calculate the bond energies, the sum of bond energies in the reactants minus the sum of bond energies in the product. So I can look into my reactants this side. I have carbon to carbon bonds. I have only one. So I have one C to C bond, carbon to carbon bond. Then I'm going to add. I have 1, 2, 3, 4. Then I have 4 carbon to hydrogen bonds. Then plus, what do I have there? I have one of this bond here, carbon to oxygen bond. I have only one. Then I'm also going to add 2.5 of carbon of oxygen to oxygen double bond. Then subtract. I have hydrogen to oxygen bonds. This time was 2, but they are already 2, so that is 4 oxygen to hydrogen bonds. Then I'm going to add, these are 1, 2, but times 2, that is 4 of carbon to oxygen bond here. So I'm going to subtract that. So carbon to carbon is 347 plus carbon to hydrogen is 4 and 3, then plus carbon to oxygen is 736, then plus 2.5 of oxygen to oxygen, which is 498. So I'm subtracting oxygen to hydrogen. Those are 4 times 468, then plus 4 times carbon to oxygen bond is 736. So I subtract that. So that means I have negative 836 kilojoules per mole here. So this indicates that the reaction here that is given the question is feasible or spontaneous because the heat of reaction is negative, indicating that the products are at a lower energy level than the reactants. So you can always comment the enthalpy change of any reaction to predict feasibility of that reaction, unless it is particular, maybe it's a formation reaction. Let's look at method 2. Method 2, we are going to use Born-Haber cycle, or we call it Hess cycle, or enthalpy cycle here. So let's dive into it. Now the general form of method 2, the cycle for when we are provided with bond energies appears like this. Reactants giving us products. So here we have atoms of elements. But they are in gaseous form, so this produces that. So for this kind of question, we are going to rewrite our equation here, but showing bonds. So this is ethanol. Then I'm adding oxygen, 2.5, we show those bonds in oxygen, giving us this is the bond shown. Then there is this, the bond shown there. So it lists the atoms that are present in all these molecules here. I can see carbon, oxygen, hydrogen, oxygen, carbon, oxygen, hydrogen. So I have carbon gaseous, oxygen gaseous, hydrogen gaseous. So let's try to balance them. So I can see that I have carbon atoms, 2 of them. So I have 2 carbon atoms. So hydrogen atoms are 1, 2, 3, 4. So I have 4 of this. So that's kind of balancing. Though this balancing is not relevant to us, what's relevant is that we are going to display the bonds leading into this. So I'll use one single arrow from this way into this, then one single arrow from this way into that. So let's check the bonds that are present. So I have one C bond plus 4CH bond plus one CO bond. Then I'm also including plus 2.5 of this bond here. So we see that as usual, we are going to have this plus this giving, because this is clockwise, clockwise, and clockwise. So I'm going to have this it value plus 4 of this, then plus 4 of this. Fact gives us this side here. That's 1 CC bond plus 4CH bond plus 1C bond like this, then plus 2.5 of this bond here. So we can feed in these values, then make this the subject. So it's going to be this side, which is 1 times, bring this way, this is 4 times auto hydrogen bond, which is 468, then plus 4 times CO bond, which is 736, is equal to 1 times CC bond, which is 347, plus 4 times CH bond, which is 413, plus 1 times CO bond, which is 736, then plus 2.5 times this bond here, which is 498. So it's the same as you making this arrow go up, then this is equal to this plus this, and all these values will be made negative. So by solving that, you arrive at the answer that we got using the other method. Let's look at example 2. Given the bond enthalpies of some bonds, the bond enthalpies, calculate the heat of combustion of ethanol. Heat of vaporization of ethanol is this value. So let's look at Hess's law by calculation. So we are first going to write our equation for combustion of ethanol. So ethanol is a liquid, burns to give us carbon dioxide and water. So we want that heat value. So carbon atoms are 2. So we have here 2. So hydrogen atoms are 6. So we have here 3. Oxygen atoms, these are 7. So this is already 1. So this is 3. So that's the equation for combustion of ethanol. Now let's expose the bonds first. So this is ethanol. Exposing the bonds in liquid ethanol. So I have 3 of bonds. Then this is 2 of these bonds. Then plus 3 of these bonds here. Now let's try to look at the bond enthalpies. So heat of combustion of this reaction will be sum of bond energies of bonds broken minus sum of bond energies of bonds formed. So in this case, bonds are broken in the reactants, but this ethanol is a liquid. Remember, bond energies involve converting the compounds that are in gaseous form to gaseous atoms. So it varies very much there. So we are going to change this to gaseous ethanol. So all the heats involved in the reactants or in the bonds formed, we shall add the enthalpy of vaporization of ethanol beside here. So let's look at the bonds. So what do I have? I have 1, 2, 3, 4, 5. I have 5 carbon hydrogen bonds. Then plus I have 1 carbon to carbon. Then plus I have 1 carbon to oxygen bond. Then I have 1 oxygen hydrogen bond. Then plus I have 3 oxygen to oxygen bonds. So I'm subtracting. Then plus heat of vaporization of ethanol. Then so this side I have 2. I have 1, 2 times 2. That's 4. 4 of these bonds. Then plus 2 times 3. That is 6 of oxygen hydrogen bonds here. So we are going to substitute in the values. 5 times carbon hydrogen bonds. Carbon hydrogen bonds is 412. Then plus 1 times carbon to carbon bond 314 plus 1 times carbon to oxygen bond 360. Then plus oxygen hydrogen bond, that is 1 times 463. Then plus 3 times oxygen to this, that is 3 times 498. Then plus enthalpy of vaporization is 44. That so we are subtracting 4 times C double, that is 743. Then plus 6 times oxygen hydrogen bond, that is 463. So let's punch in the calculator. Negative 979 kilojoules per mole. So that indicates that the reaction is very, very feasible because the heat of combustion or the heat of that reaction is exothermic. Let's try to use another method, but try to do double check of this. There can be calculator errors here and there. So let's now try to use Hess cycles or Born-Haber cycle. So for this case, we have to just identify the atoms, the gaseous atoms from the elements. So I have carbon, hydrogen, oxygen. So I have carbon, gaseous, hydrogen, gaseous, oxygen, gaseous. So all this side falls into that, this side liberates into that. So I'm interested in the heat of combustion of that reaction there. So for this side, we must add the heat of vaporization, since we have seen that this is liquid ethanol. So the bonds present there, this side, we just have to look at 2, this is 2, but times 2, that is 4 of CO. Then plus, this is 3 times 2 of this, that is 6 of oxygen hydrogen bonds. Then under this side, 1, 2, 3, 4, 5, that is 5 of carbon hydrogen. So I'm going to add it to 1 of CO. Then I add also 1 of OH. Then I add also, this is 3 of oxygen double bond. So basically those are the bonds. So I hope I've not left out anything. So I have 1 C bond. So we are going to look at this heat of combustion. So we said you can either get this plus this equal to this, or you just change this arrow, then make all these heats negative. So it will be this is equal to this, it bonds plus this bonds plus OH is 1 plus double 1 plus CC bond here. Then you are just going to subtract to add the negative of this, 6 of this. So because the arrow has been reversed, otherwise we would add normally this plus this, the arrow is pointing down, and the answer is going to be actually the same. Let us look at the next category here. Now in this category, we are finding the heat of a reaction given bond energies and atomization energies or bond dissociation energies. So But what's going to be very important are the atomization energies here. Now, if we are given bond dissociation energies, we are going to convert them to atomization energy by dividing by 2. So bond dissociation energy is twice atomization energy. Atomization energy is a half bond dissociation energy. The method we are going to use that's more suitable here is the use of Born-Haber cycle, or we call it the Hess cycle. Now, this is how the method looks like, how the cycle looks like. So it will contain reactants to give us products. Now, both of them will be able to change into gaseous atoms, and this also into gaseous atoms here. Let's dive into the question. Calculate the enthalpy of formation of chloromethane using the following thermochemical data. Now we're interested in formation of chloromethane, so we are first going to write the equation for formation of chloromethane. So chloromethane is formed from carbon, hydrogen, and chlorine here. Carbon, hydrogen, and chlorine to form chloromethane gas. If you don't know the states, you can as well leave them out to avoid errors. Now let's balance it. This is 3 out of 2. This is a half. Now let's atomize them into gaseous atoms. Here I'll have carbon gas. I'll have hydrogen gas from here. Then I'll have chlorine gas from here. But let's first balance down these atoms here. I have 3 out of 2 times 2, which is 3 atoms. Here you have 1 atom. So this will also dissociate down. Now when you are breaking this into the gaseous atoms, you are applying energy. So the values are positive down. In case you reverse the arrow to show that you are forming this from these formation values will be negative. So let's dive into that. So we are looking for this value, formation value. Now carbon to gas, because this is a solid, we call it sublimation energy, or sometimes they can leave it as atomization energy. Sublimation energy of carbon is 715, so you put the respective sign. Now, they have given us bond dissociation energy for hydrogen, so we first convert it to atomization energy, divide it by 2, so it will be 435 out of 2. But because atomization energy is the energy required to form 1 mole, so I formed 3 moles here. So I will multiply this value, which is atomization energy, by 3. So instead, we can write it in a better way as 3 out of 2 times 435. Times 435. Then for chlorine, bond dissociation energy of chlorine is 248. But divide it by 2 to make it atomization. Then look at the moles here. I have 1 mole, so it is kept like that. So how many bonds in chloromethane? So chloromethane has 3 of carbon hydrogen bonds, then has 1 carbon chlorine bond, which is this bond here. So that's it. Let's feed in the energy values here. So we look at all arrows going clockwise and add those going anti-clockwise. So I look at this and this in the clockwise sense, then this and this and this in the anti-clockwise sense. So this plus this is equal to this and this. So this formation value plus 3 carbon hydrogen bond plus 1 chlorine bond is equal to 715 plus 3 out of 2 into 435. Then plus 248 out of 2. So substituting this value, enthalpy of formation plus 3 times the carbon hydrogen bond. Carbon hydrogen bond is 413. Carbon chlorine bond is 336 times 1, giving us 715 plus 3 out of 2, 435 plus 248 out of 2. So compute that value and you'll arrive at negative 83.5 kilojoules per mole. Now this indicates that chloromethane is very stable because it's formed exothermically here. Now some students can face a very big challenge in interpreting these arrows here. You can make sure that the formation value, this single arrow is equal to other steps added together by making sure that these arrows go in the same direction. So this is going anti-clockwise in the clockwise sense, these are anti-clockwise. So we can reverse this arrow. So when we reverse this arrow, all these values are going to be negative. Don't need to indicate a negative here, but we shall indicate a negative respectively on the energy values when we are substituting them there. So let us try to use the other alternative method. So we can as well say the formation value is actually equal to this 715 plus 3 out of 2, 435 plus 248 out of 2, then minus, so these are going to be negative 3 times carbon hydrogen bond 4 and 3, then also this negative times 336. That right away gives us negative 83.5 kilojoules per mole, the same answer there. Let us look at example 2. The enthalpy of formation of phosphorus trichloride is this, and enthalpies of atomization of phosphorus and chlorine are this and this. Calculate the average bond energy in this. Let's first write the equation for formation of phosphorus trichloride. So phosphorus trichloride comes from phosphorus, which is a solid, plus chlorine, giving us PCl3. So let's balance this. So here I have 1 phosphorus, put a quarter. This put 3 out of 2. So this is the formation value, which is negative 306 here. So let's look at converting this to a gas atom. So don't put a 4, make it a molecule. So this is atom also, but a quarter times 4 is 1, 3 out of 2 times 2 is 3. Then this dissociates down into that. So let's look in the question. The enthalpies of atomization of phosphorus and chlorine are this and this. Phosphorus is positive 314 because I have 1 mole here, but for chlorine, atomization energy is 242. In fact, this is 12121. So that is atomization. Since I formed 4 moles here, I will multiply by 3. This 3 is because of forming 3. So this will be positive value, 121 there. Now here there are 3 bonds of PCl, so I have 3 phosphorus chlorine bonds there. So as we agreed earlier, we can either maintain this arrow to face down, or we can make this arrow to go up there. So any order here, so we can have this plus this. So it can be negative 306 plus 3 PCl bonds. These are both clockwise, is equal to 314 plus 3 into 121 here. So it's solve for PCl bond there, punching that value. So that is, so this is 327.667 kilojoules per mole. This is positive. It's positive because the arrow is facing into dissociation. Alternatively, another student can reverse this and make this arrow go up. Then we agreed that if that arrow is up, then this is equal to all these ones, because this and this are anti-clockwise. So negative 306 is equal to 314 plus 3 into 121 plus 3 into PCl this. So I solve for this. PCl that will give us negative 327.667 kilojoules per mole here. That means if you face the arrow up, the value is negative. So both of the values are correct. Let us look at the next category here. Now in this category, we are looking at energy level diagrams and Born-Haber cycles. Energy level diagrams and Born-Haber cycles. Now an energy level diagram is different from a Born-Haber cycle, but a Born-Haber cycle can be an energy level diagram. So if you asked it specifically for energy level diagram, you draw a diagram where some arrows go up and some go down. Positive arrows going up represent positive energies. So let's dive in this example to see more of this. Some thermochemical data of copper 2 chloride and chlorine are given below. So this is the data. Calculate the lattice energy of copper 2 chloride. Now, Born-Haber cycle was developed to use in the calculation of lattice energies for ionic solids. So let's first look at the energy level diagram, then also look at Born-Haber cycle. We can also attempt the same question by Hess's law using a calculation, not necessarily a diagram. So let's look at energy level diagram. So energy level diagram here. So you can draw it in any way that you may prefer. So we can draw a simple one this way. So this is, can widen it a bit. So this is copper plus chlorine gives us copper 2 chloride. This is a solid. Its energy is negative 2 to 0. The enthalpy of formation of copper 2 chloride. So we first convert copper to a gas. Copper to a gas plus chlorine, don't touch chlorine. Then the next stage, convert copper into one gaseous ion. Don't touch chlorine. So we reach copper with a positive 2 charge. That's second ionization energy. So you don't touch chlorine. Then finally we can work on chlorine here. So copper 2 ions, gaseous, plus this chlorine molecule, we can break this bond, then form 2 chlorine gaseous atoms. So this is it, chlorine gaseous atoms here. Now we give it a charge, so being that the first electron affinity is negative, so I'll slope a bit down. So this plus 2 chloride ions here. So these energies are positive, arrows are facing up, this faces down, then this is faces down. So this is the lattice energy. Now this can represent energy axis, so kilojoules per mole. Then this is the 0 point. Then this can be reaction path. Now let's look at what the question has given. Sublimation of copper is plus, so this is positive 338. First ionization energy of copper is plus 745, include these signs. Second ionization energy 958. Now we look at the Venus bond dissociation energy of chlorine. I always advise when they give you bond dissociation energy, first convert it to atomization energy. It is easier to interpret atomization energy. So atomization energy is got by dividing bond dissociation energy by 2. So roughly I'll divide 242 out of 2. Then this means I will have got atomization energy. Now at this stage here, you look at how many moles do you have here. I have 2, so atomization energy is for 1 mole, so I would multiply this by 2 because of these 2. So this value will remain like this. Or rather, you can interpret that having 2 molecules and you form 2 molecules, this is called bond dissociation energy. That would be interpreted that way. But the easiest way is to first convert it into atomization, then finally put with respect to this value that is attached on the gaseous atom there. Let's look at the first electron affinity is negative this. So first electron affinity is for 1 mole. These are 2, so you are going to multiply this by 2. Negative 364. So we can now look at all arrows going in one direction are equal to those going in the opposite direction. So I have this negative 220 is equal to this value 338 plus 745 plus 1958 plus 242 plus 2 times negative 364 plus lattice energy here. So we make lattice energy the subject. So put it in the calculator. So this gives us negative 2775 kilojoules per mole here. Let us now look at the Born-Haber cycle. Now in the Born-Haber cycle, we first write the equation. So this is Born-Haber cycle. So we write copper plus chlorine gives us copper 2 chloride is a solid. So the equation is balancing. So this is the formation value, which is -220. So first convert copper to a gas, then first ionization energy, then second ionization energy. So I can handle, let me try to adjust this. Gas, first ionization energy, then second ionization energy here. Then chlorine, I first atomize it, form 2 gaseous atoms, then give it a charge, then put a addition here. So you look at this value for copper. Sublimation energy of copper is about positive 338. First ionization energy 745. Second ionization energy 1958. Then bond dissociation energy, or rather atomization energy divided by bond dissociation over 2 times 2, which is the same as this is the bond dissociation energy because you have formed the 2 from 2, or rather we divided it by 2 then multiplied it by 2. Interpretation of atomization energy. So this is times 2 for electron affinity, since we have formed the 2 moles of gaseous atoms here, gaseous ions rather. So then we face into this. We can as well say this. So you can draw like that, or you can draw just from here like that. So this is the lattice energy. So we shall see this value going in the clockwise sense is equal to all these arrows going anti-clockwise. So it's -220 is equal to this value 338 plus 745 plus 1958 plus 242 plus 2 times -364 plus lattice energy. So lattice energy is actually going to be -2775 kilojoules per mole there. So that is the lattice energy. This is called Born-Haber cycle. But we said if the question says Born-Haber cycle, you can draw this or draw energy diagram. But if it says energy diagram, you can't draw this. You draw the energy diagram. Let us look at part B of this question here. So in part B, they are saying the hydration energy of copper 2 chloride is this. Determine the enthalpy of solution of copper 2 chloride. Let us first show how copper 2 chloride dissolves. Copper 2 chloride solid will change in water. It will appear as ions in aqueous state after dissolving, but this process first goes through a stage of forming gaseous ions. So first form gaseous ions, then these ions undergo hydration here. So we have, this is the enthalpy of solution, delta, standard value, solution. Then this one is the breaking the ionic bonds to form gaseous ions called the lattice energy. So this is lattice energy. Then this is giving the ions aqueous state. So we are hydrating them. This is hydration energy. So we are going to have this value is equal to these arrows which go in one direction, that's anticlockwise. So enthalpy of solution, enthalpy of solution is actual lattice energy plus hydration energy. Now we see that this solid is dissociating into ions. So if ions were combining to form this, it would be negative, but this, you are using energy to dissociate this into ions, so the value will be positive. So lattice energy in this case is going to be positive 2775. Then this one is going to be, according to the question, it has given us 2883 here. So we are going to just punch into this. So this is 2775 plus negative 2883. So it gives us negative 108 kilojoules per mole. Now this value has information about the solubility of copper 2 chloride. If the value is exothermic or negative, then copper 2 chloride is a soluble salt. If it is endothermic, if it's positive, then copper 2 chloride is an insoluble salt there. This same question can be done using the Hess's law by calculation like this. Now to use Hess's law by calculation, part A, for calculate the lattice energy, we are going to first write out equations for this information. Enthalpy of sublimation of copper. So here we are looking at next method, Hess's law by calculation. Hess's law by calculation. So we've used the energy level diagram, Born-Haber cycle. So let us see how we use Hess's law by calculation. So sublimation energy means converting copper solid to copper gas. This value, and that value is actually positive 338 here. Then enthalpy of formation of copper 2 chloride. So you form copper 2 chloride from its elements in their standard states or normal physical states. So you form this solid. This value is, can call it heat to negative 220. Then first ionization energy of copper, that's converting gaseous solid into copper 1 ions plus an electron. This value is actually positive 745. Then the next second ionization energy of copper, you start from the first, the gaseous ion, convert it into a charge of +2, then +2 electrons to balance, plus an electron rather, balance the equation. So this is, delta enthalpy 4 is actually positive 1958 there. First electron affinity of chlorine, that's converting gaseous atoms 1 mole into gaseous ions by adding an electron according to the definition. So here you are getting negative 364. Then bond dissociation energy of chlorine, that means you are converting, you are breaking a bond in chlorine molecule to release it into gaseous atoms. So remember that bond dissociation energy, if you have 2 atoms in the molecule, then you dissociate from those number of atoms in the same molecule. Of course, if it was atomization energy, we would put a half here to form 1, because that would be for 1 molecule. So this is delta 6, which is positive 242. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's look at calculate the lattice energy. So let's write the equation for lattice energy. So the lattice energy, we are going to combine gaseous ions, because the energy released when gaseous ions combine to form 1 mole of an ionic crystalline solid. So combine the gaseous ions to form that. Or rather, this value now must be negative after calculation, but if you dissociated this into gaseous ion, the final value will be positive. So let us write about it here. Let us now. So we are going to manipulate. So we are needing this heat here called the lattice energy here. So we are going to manipulate all these equations to arrive at this one here. So you can do it mentally and just write the expressions for equation 1, equation 2. You can call this equation 1, equation 2, equation 3, equation 4, 5, 6. Now it's better to follow what appears on the equation as we manipulate. So I have copper 2 ions on the left. So I look at this equation that has copper 2 ions. So I'm going to reverse this. So this is going to be negative of equation 4. So let me first write it here. So negative equation 4. So that means I have reverse equation. So copper 2 gas plus an electron gives me copper 1 ion gas. So this delta value is going to be negative. So this is going to be negative delta H4. So let me look at this other equation. Chloride ions are appearing on this equation, but I must do reversed. So I'm going to also subtract equation 5. Equation 5. Subtracting means I'm reversed, so I'm multiplying it by 2. So 2 equation 5. So I reverse that. So 2 chloride ions, then multiply this by 2 reversed. So it will give me 2 chloride gaseous atoms plus 2 electrons here. So this is negative delta H5 like that. I can also observe this one. So I've dealt with equation 4. I've dealt with this. I've also dealt with equation 5. So copper 2 chloride appears on this equation here. So I can bring this down. So I'm not reversing that. So plus equation 2. So I bring it down here. So copper plus chlorine gives us copper 2 chloride. Then this value remains the way it is, positive delta H2. So I will not reverse that. So this is done. So I'm left with this equation. So we can see that chlorine has come in here. So I have to reverse this one here so that it will cause this to cancel. So minus equation 6. Minus equation 6 here. So I reverse this one. So I start with this side. 2 chloride gaseous atoms gives us chlorine this. Then this is negative delta H5. So what again have I created in here? I've created in this copper, so this is done. This copper here is in this equation here. So I must do away with this copper here solid, but I also have copper here. So this is going to help me cancel this ion here with this single ion here. So I'm going to reverse this equation here. So minus equation 3. Minus equation 3. So I reverse that. So it is copper 1 ion plus electron gives me copper gas. So delta H3 reverse this. But I can see here I have copper gas. So this equation here must be reversed so that it helps me to cancel this. So I'm going to also reverse this. So I will say minus equation 1 here. So this is going to be copper gas to give me copper solid here. So this will be delta H1 reversed. So when we add all those equations there, we should be able to get this required equation here. So this is the required equation that we shall get at that point there. So you can cancel what we do not need. So we can see that I have chloride. This electron and this electron will cancel with these two. Then I have chlorine gas here, will cancel this chlorine gas. I have this, will cancel with this. I have copper 1 ion, will cancel with this here. Then I have copper solid, will cancel with this. Then I have copper gas, will cancel with this. So ideally, I think you can see that we have arrived here. So you shall just sum these energies the way they are accorded here. So we can feed in these energies. Energy 4 reversed is this, -1958, plus energy 5 reversed. 5 is this one, so it's +364. But this one we multiplied it by 2 because of this 2. So this is times 2. Then plus energy 2 remained as it is, that's negative plus -220. Then plus energy 6 reversed, which is -242. Then plus negative energy 3, -745. Then energy 1 also reversed, which is -338. So you can look at this total value, which gives us the same value, -2275. So you put here the equation that because of space I've tried to use this other part here. That's how you use Hess's law by calculation. Let us look at heat of neutralization. Right away dive into the example. When 50 cubic centimeters of 1 molar sulfuric acid at this was mixed with 50 cubic of 2 molar potassium hydroxide at this, the temperature of the mixture rose to this value. Calculate the enthalpy of neutralization. We start by finding the total volume of the solution. So total volume, we got 50 times 2, which is 100 cubic centimeters because I'm using 50 and 50. So mass of solution, I'm having the volume times the density, which is 100 grams. Then let's look at temperature change. I'm looking at the final temperature or the maximum temperature minus the initial average, 13 degrees Celsius. Now let's dive into finding the heat evolved. We're going to have this used in the formula because the temperature also the heat was given out. Now the mass is 100, specific heat capacity 4.2, temperature change 13. So patching it the calculator, we get 5460 joules. Now at that stage, we go and acknowledge, because we are interested in finding the number of moles of water produced in the reaction. So we acknowledge this ionic equation. So we can either find the number of moles of sulfuric acid or potassium hydroxide, but consequentially we must find the number of moles of water. So let's use hydrogen ions here. So number of moles of sulfuric acid, that's going to be 50 times 1.0 out of 1,000. So this is the molarity used, 0.05 moles here. Now, since our equation has hydrogen ions, we must look for the number of hydrogen ions in 1 mole of sulfuric acid. So ionized sulfuric acid. So we produce this. So then molar ratio of sulfuric acid to hydrogen ions is 1 to 2. So number of moles of hydrogen ions are actually going to be 0.05 times 2, giving us 0.1 moles there. So from the equation, mole ratio of hydrogen ions to water is 1 to 1. So we can also look at that. Mole ratio of hydrogen ions to water is 1 to 1. So number of moles of water produced, number of moles of water formed will be equal to, because it's the water that absorbs the heat of the reaction and the temperature of the water increases. That's why we're interested in water very, very much. So formation of these moles of water produces this. So formation of 0.1 moles of water produced 5460 joules of heat. Water formation of 1 mole of water, formation of 1 mole of water produced this out of 0.1 joules. That gives us 54600. So enthalpy of neutralization is actually going to be 40. This value in joules, but with the negative, because heat of neutralization is negative. You can leave it in joules or divide it by 1000, write it in kilojoules per mole. Let us look at enthalpy of displacement right away into the example. When excess magnesium powder was added to 50 cubic of 0.2 molar solution of iron 2 sulfate at this, the temperature of the mixture rose to this one, determine the enthalpy of displacement. Of course, specific capacity of the solution should be given as it is 4.2, then density of the solution is assumed to be density of water, which is actually 1 gram per cubic centimeter. So we should acknowledge that even if they gave the mass of magnesium powder, it's always in excess, and it's the solution acting as a limiting reagent. So we ignore this mass always there. So let's right away get the mass of the solution. Mass of the solution is going to be 50 times. Of course, we are going to make assumptions. Density of solution is equal to 1 gram per cubic centimeter. Specific capacity of the same solution is equal to 4.2. Then mass of solution will actually equal to 50 times 1, giving us 50 grams. So let's look at the temperature change. Temperature change is actually 40.0 minus 30.5, giving us, that's about 9.5 degrees C. Now let's look at the heat given out here. Heat evolved or heat change is equal to mass, like that. So the mass is 50. Specific capacity 4.2, temperature change about 9.5 and 99.5 joules. So these are the joules of heat produced there. Now we look for the number of moles of the solution used. So number of moles, iron 2 ions will equal to 50, 0.2 out of 1000, so 0.01 moles. So we are interested after magnesium is added to iron 2, it displaces iron. So we are interested in the number of moles of this iron that have been displaced, this one here. So mole ratio of this is 1 to 1. Mole ratio of iron 2 to iron solid is 1 to 1. So number of moles of iron is the same here. So displacement of this produces this. So displacement of iron, displacement of 0.01 moles of iron produced 1995 joules. Or formation of this produced that. So displacement of 1 mole of iron produced 1995 out of 0.1. 0.01, this is 1995 joules. So enthalpy of displacement, since the temperature rises, the negative 199 joules, which is going to be negative 199.5 kilojoules per mole. This is per mole here. Let us look at the heat of precipitation. Now, 50 cubic of 0.1 moles of silver nitrate was added of silver nitrate solution at 29 point this is added to 50 cubic of potassium chloride at this. The mixture was stirred and the highest temperature reached was this. Calculate the heat of precipitation. So what we first do there is to look for the total volume. So look for total volume. That is, each is 50, so this is 50 times 2, giving us 100 cubic centimeters. Then the question, though it has not given us information about density, but the assumptions are that density of the solution and density of water is the same, and specific heat capacity of the solution and that of water is the same. So we are going to use mass of solution. Mass of solution, we are just multiplying this by the assumption we made. That gives us 100 grams. So let's look at temperature change. Temperature change. We are simply going to look at the final temperature, which is 32, minus the average initial temperature, 29.5 and 28.5, out of 2. So we get that here, we get about 3 degrees Celsius. So next thing is to get the heat change. So heat change, because silver nitrate, the temperature rose to this one, so that is the heat evolved or heat change. So heat evolved. That will be basically now the mass mc delta theta. So that is the mass 100. We assume the specific capacity of water to be the same as that of the solution formed of the mixture. Rather, so this is times 3 at 1260 joules. That is the heat liberated. So we are going to write the equation and see how we form the precipitate. So we have silver nitrate. That means I have silver ions, aqueous. I'm adding chloride ions from potassium chloride to get silver chloride. This is the precipitate formed. So we must look for the number of moles of the precipitate using moles of N of this, since the moles of both of N of this is the same according to the information in the question. So we are first going to look for the number of moles of silver ions. So number of moles of silver ions, that's going to be 50 times 0.5 out of 1000. These are 0.025 moles. Now from the mole ratio, 1 mole of silver produces 1 mole of silver chloride PPT. So mole ratio of silver ions to silver chloride is 1 to 1. So number of moles of silver chloride are the same, 0.025. So these are the moles of the PPT form. So formation of 0.02 moles produces this. So precipitation of 0.025 moles of silver nitrate produces 1260 joules of heat. What of 1 mole? What of 1 mole of precipitation of 1 mole of silver chloride produces, that is this one out of 0.025 joules of heat. This is 504000 joules. So heat of precipitation is negative. Heat of precipitation be negative this value in the joules because it involves the liberation of heat.